Hello and welcome to ESCT 0100. Today we're going to be talking about electrical, mechanical, and instrumentation systems. Each of these three systems are going to be prevalent in just about any power system you encounter. So we're going to break them down today and we're going to talk briefly about each one. So we'll start with electrical. So when we think about that grid, as we go from the generation system to the transmission system to the bulk power substation, and then we break that out into all these different sub-transmission and distribution voltages. These are everything that will take us from an industrial load to a commercial load down to your 120 volt residential load. So the grid is really nothing more than this combination of generation, transmission, and distribution. So all of that integrated into a system makes up that thing that we call the electrical grid. Within a plant, we're going to typically have some sort of power distribution diagram. And if you think about a plant, it could be a plant that makes potatoes, potato products, something that makes microchips, refinery, something that makes plastics, something that makes any device, any food product, any equipment that you can possibly imagine will all have some sort of power distribution system, and it's going to be something that is going to be explained with a power distribution diagram, and it's going to typically be just like this one-line diagram right here. And again, this is a one-line diagram that shows you in a notional kind of way or a conceptual way that we're feeding power in from the power company. We've got a transformer outside. We've got an electric meter to actually give us a billable number so we can get a bill from the power company. And then we have a distribution panel. And that distribution panel, in turn, sends power out to all of the different loads that exist within the plant. This same basic system is something that you would encounter in your home. You would encounter it in school. If you go out and you look at the STEC building and you look at that area between the STEC building and the Trade and Technology building, you'll see some transformers. If you go over and look in front of the Rendezvous Center, again, you'll see some green pad mount transformers. So these are the transformers that are shown as the transformer. In this case, outside, they almost always are. And the transformer is simply going to be a series of windings, and when you get to the AC discussion in your electronics classes, we'll spend more time talking about transformers, but they're simply sets of coils of wire, and based on the ratios of the number of turns of wire in the primary and the number of turns of wire in the secondary, we can increase or decrease voltage. However, remember that when we change voltage, we also retain a change in current. So we have this formula that says power equals voltage times current. Well, since the transformer doesn't create power, it just transforms it, it means that the mathematic sum has to be the same. So if I increase voltage, I have to decrease current to keep the power the same. What a transformer does for me is it lets me increase the voltage when I'm transferring the power, because as I'm transferring the power, I have lower current, so I have lower I squared R losses in the lines. That makes the system more efficient. And then when I get to where the load is, I can drop that voltage so that I can have less of a danger of arcing, so I don't have to have really high voltage in my house. It would be kind of an interesting challenge to have 4,160 volt appliances. They would work just fine, but they would be huge because of the insulation required. So we reduce the voltage, we increase the current, and we're able to reduce the insulation as a result. So do take a minute, walk around ISU, look just outside the STEC building or over at the Rendezvous Center, note those transformers. and realize that there's a drawing very like this distribution diagram for every building on campus and every manufacturing plant that you might ever encounter. Inside a large manufacturing facility or power plant, you're going to see a motor control center. Not all motor control centers are this big. We have motor control centers downstairs in this building, and those motor control centers are slightly smaller than these, but they all perform essentially the same thing. A motor control center is simply the place where power comes in through a protective device that you'll learn about later, and you'll actually put one together in lab. The motor control center gives us a way to stop and start the motor, and to do so while we have additional protections that are more advanced than the simple system of using a switch that you might use to turn on a light bulb, as an example. Motor control centers provide a way to distribute power, to do so safely, and to provide additional protections for the motor loads that are connected to the system.
So the wires that connect all of these devices have to be protected. Wires are typically covered with some sort of insulation, which provides electrical protection, but not mechanical protection. So we're going to use conduit. And here you see several different types of conduit. Each of these has its own purpose. On the far left, we see what's called rigid conduit, and it's really just like a pipe. You know, if you pick it up and feel it, it looks like a galvanized pipe. It feels like a galvanized pipe. It's got a thick wall. You can physically thread the pipe just like you could a piece of water pipe, as an example, and it provides really good protection. It is, however, difficult to run, and in a lot of cases we don't need anything quite that robust. So we can use EMT, or electromechanical tubing. In the next couple of examples there, going sort of to the middle of the photograph, you see some examples of electromechanical tubing. Electromechanical tubing is much thinner, so it's easier to bend. It's also lighter. But because it is so thin, we can't thread it. So we use a mechanical fitting like the ones you see there that are attached with a screw. Essentially, you position it over it, you tighten the set screw, and it holds it together, and it provides a good mechanical connection, but it's not as robust as the threaded fitting you see on the far left. To the far right, you see two different types of flexible conduit. Flexible conduit can either be sealed, which is the kind of the gray one that has the blue end on it. So that could be gas tight or watertight, and could be used in a moist environment or a gaseous environment where you might have an explosive vapor. The one on the right isn't sealed. It just provides some flexibility. Now, one of the reasons we need some flexibility is sometimes we're actually connecting to something that moves. It might move a lot, or it might just vibrate slightly. But if you have that mechanical movement on something all the time, it will fail. So you have to have something that's designed for flexibility, and that's what the flex is used for. We also have to actually get power from the switchgear, which is the electrically switched source of the supply to the load itself. And to do that, we're going to use Busway. Busway, sometimes called bus duct, comes in a lot of different flavors. This is sort of a stylized version of it, and in later lectures we can talk more about all the different types, so I'll just sort of describe them and you can reflect upon the descriptions. The descriptions are pretty self-evident. There is segregated buswork. Segregated buswork has each of the phases inside the bus physically separated by some sort of electrical barrier. There is non-segregated bus duct, which is where all of the phases are separated only by space. There is no physical electrical barrier. We also have cable bus, which is just exactly what it sounds like. It's multiple phases of power, all connected with cables rather than bus bar. And lastly, we have gas insulated bus. Gas insulated bus typically just looks like a pipe, and the pipe is full of sulfur hexafluorine gas. Sulfur hexafluorine, sometimes called SF6, is a very good insulator. So you can have a very high voltage insulated by sulfur hexafluoride gas, and because it is such a good insulator, it allows you to have a much more compact bus, particularly when you're running high voltages above 138,000 volts. Ultimately, we're going to have to connect this to some loads. Well, here's one of the most common loads, an electric motor. There are literally hundreds of different types of electric motors. They come in all sorts of sizes and all kinds of shapes that operate on all sorts of different theories of electrical operation. But this is a pretty typical one, and what it has in terms of its parts are pretty typical of many, many of the common designs. So we have an end bell, which also supports one of the bearings. You can see the bearing on the opposite end of the shaft as well. It's actually labeled. The shaft just simply passes through the motor. It turns on those two bearings. It has a rotor, and surrounding the rotor is the stator. So as we apply voltage, we get current flowing through the rotor. We can that's usually induced from the stator. It causes electrical currents to produce electromagnetic forces, and thus the motor turns. This really isn't a discussion about motor theory. We'll get into that later. But all of these fundamental parts are things that you're going to see all over the place, running pumps and moving conveyors and lowering doors, lifting doors, moving product of all sorts in just about every environment that you can imagine, and just about in every sort of factory you can imagine. And in power plants, we're going to primarily use these things to move fluids, because we're typically going to be using fluids, most likely water, as a thermodynamic medium to move heat around. And so in a power plant, we'll see lots of pumps driven by lots of motors. Those motors have to be grounded. Grounding is a safety measure. If the case of the motor should become energized and you were to touch the case, the path of ground would be from the motor to you, and you would receive an electrical shock. So to prevent that, we ground the case of the motor to earth ground. So in this diagram, you see that there's a green wire coming up, going up into the service panel. There's a jumper, that's a bonding main jumper that takes that connection back outside the building, into this case, and actually into a ground electrode that's essentially a copper rod that is physically driven into the ground. So should there be a fault inside the motor, the electrical current would flow away from the motor case would not be at an elevated electrical potential, and the possibility of electrical shock would be eliminated. I mentioned the motor driving a load earlier, and in this case we see a pump. So this is really where we start putting a system together. And the system is just something that consists of more than one part. So here we have a motor. The motor is connected through a shaft and a coupling to the pump. The pump itself rotates and is pumping some fluid out in some direction. We have a electrical circuit up above that is providing a physical connection through conduit, the same kind of conduit we looked at before, to the motor. And we also have a sensor on the suction of the pump, which could be measuring flow as an example. And it too is connected with conduit to a panel, and both of those are going off to some system. Most likely the power side is going off to a motor starter somewhere, and the signal from the transmitter would be going to a control device somewhere. But this is the beginning of a motor coupled to a pump. To operate it, we're going to need some sort of switch. a real common switch is a push button switch. This particular push button switch that we have as illustration here is the type of switch you would usually use in an emergency situation. So you see it has a big red operator head, that's called a mushroom head. And that would be a switch you would use as an emergency stop because it has a real easy to operate head. You can just push it with the palm of your hand, and in this case, you could stop an assembly line, you could stop a pump, you could stop a motor from running. So there are all sorts of switches. I said there were hundreds of different types of motors. There are thousands of different kinds of switches. So we're just going to look at a couple of them here. Here we have some lever switches, a fork switch, a roller switch, a wobble stick. All of these could be used in some sort of process. There are literally, as I said, thousands of different types of switches, but essentially they're going to do one thing. They're going to either open or close a contact. And so we're going to use a phrase here of normally open contacts or normally closed contacts. A normally open set of contacts is a contact that when you hold the switch in your hand, there is no continuity. In other words, there's no connection from the input of the switch to the output of the switch. The switch has to be operated to go into a condition as this, for instance, you push the button and the contacts close. That's a normally open switch that is closed when you push the button. And since you have to actively push the button, so it's not in its shelf state anymore, we would say those are normally open contacts. The reverse of that, normally closed contacts, would be when we hold the switch, the contacts are closed, so there's continuity from the input to the output of the switch. And if we want to open the contacts, we have to hold the button in to open them. In this case, we would say that's a normally closed set of contacts. And how and when we use normally opens and normally closes are things we'll talk about in the future, but these are words that you're going to get used to and understand how you use the right kind of switch in the right application to get the result you're looking for. Here's an example of a float switch, another kind of switch. The float rises and falls. The switch is in the little box in the upper right, and that's going to be connected to some sort of device, most likely a pump, to stop and start. And as the float rises and falls, the pump will turn on and turn off, maintaining the level in the tank at the desired level. So once again, a real specific example of having the right piece of equipment to achieve a particular. Another type of switch, this one's a little different. This one doesn't have moving parts. This is a proximity sensor. So instead of actually touching it, it uses some electronics to measure the proximity of a substance. So most typically, it's going to measure the proximity of some sort of metal device. So if you had, as an example, a metal Coke can moving down a filling line, you would want to be sure that you are actually putting product in the can, not on the floor. So this device could determine that the can was directly in front of the fill nozzle and would then dispense the product. The thing about this is, you see, it has no physical contacts. It's going to operate purely electronically with no moving parts. Yet another type of switch. This is a capacitive sensor. This is the type of device you would typically see. And without getting into a whole lot of discussion about how this works, essentially we have a system that looks at the capacitance. In other words, the difference in charge across a dielectric force. Dielectric is just a really cool word for insulated. So we look at the different voltages as they're coupled across an insulator, and that gives us a capacitive field. And if you look at the diagram, you can see that we have this target that has some sort of dielectric constant, and as long as the dielectric constant is less than 1.2, and that's just a measure, we'll talk about how that works later, the switch doesn't activate. If we have something that has a higher dielectric constant, a piece of metal as an example, then it does activate. This is a use of a switch that has no moving parts, nor does it actually have to make physical contact with what it's sensing to turn it on and off. Lastly, we have laser sensors, and laser sensors are optical. Again, they're electronic. They don't require any physical contact. They are going to work on the basis of light and light reflection and refraction. So a laser sensor can also sense the presence of something, but because it doesn't have to have this dielectric component, it can look at a lot of other things. So rather than being confined to things like metal, as an example, it can look at plastics, it could look at food products like a potato or wheat, it could look at pieces of paper, it can look at a lot of other things that don't react with a capacitor, but could be seen and therefore would interact with light. So these are just some of the basic examples of switch types.